Okay, so here's a quick demo of the OpenLogic project. So here I have given myself some premises. I have P implies Q, I have R or S, I have T and not Q, and I have P if and only if S. And then I formed a conclusion that I want to try and derive. I want to show not P and Q if and only if S, and either R or P and T implies R. So I put all that in, I click create problem, and it gives me the problem as it is here. So then I can start trying to derive things. I see that this is overall a whole bunch of statements that are going to be true, so I want to try and derive each one separately. So I might start by seeing not P, and so I can think about how I want to get that. I know that P implies Q, and not Q is true. So if I want to assume P and then start working from there. So I'm going to start a new subproof. I will assume P, and that's an assumption, so it doesn't need a citation. Once I have P, I can derive Q, and that is done using arrow elimination on lines 1 and 5. And I can be like, did I do that right? Check the proof, please. And it'll tell me, I haven't made any errors, but I haven't reached the conclusion. So that gives me Q, but I also know not Q, so I could say not Q. And that is going to be and elimination on line 3. And so you'll notice also that when I type in and here, I'm using an ampersand, and it autocorrect it to a wedge like that, which is nice. We can keep going. Putting in double X gives us a contradiction, and that is derived using negation elimination. Tilde is used for negations. Negation elimination on lines 6 and 7. And that's actually going to finish a proof by contradiction, which means that we can finish the subproof and add a line, because we're going out a level, and that gives us not P, and that is going to be derived through negation introduction on the proof from 5 to 8. So that's basically just proof by contradiction. We assumed P, did some derivations, and derived a contradiction. So we got not P. That was the first thing that we had as a goal. Next we want to get Q if and only if S. So the way that we generally find biconditionals like this is we assume one, derive the other, and then assume the other and derive the first one. So we're going to start a new subproof. We're going to assume Q, and we need to somehow derive S. Well, we also know not Q, so this case can never happen. It's contradictory. So we can show that. Not Q. And that's going to be and elimination of line 3. And at this point you might actually notice, oh, it might have actually been more efficient to do this derivation of Q at the main level of proof, and then we wouldn't need to keep redoing it, but we didn't catch that, so it's fine to just take the long way. Once we have not Q, we have a contradiction. That's going to be negation elimination on lines 10 and 11. And from a contradiction we can derive anything, and the goal that we said we wanted to get was S. So let's take S, and that's going to be through the X rule on line 12. And just to check that we are still making good progress, we're still all good. No errors yet. So that shows that if you assume Q, you can derive S. We also need to show that if you assume S, you can derive Q. So we want to finish this subproof and then start another one. So let's assume S. And we know that S is true if and only if P. So we could get P, and that's through biconditional elimination. And this kind of like angle bracket with the dash there is how you draw your arrows, both biconditional and conditional. And that's going to be on lines 4 and 14. This is the biconditional. This is the thing that we're eliminating out of it. Once we have P, we also have P implies Q. And so we can get Q. And that's going to be arrow elimination on lines 1 and 15. and that gives us, we assumed S, and we somehow derived Q. So that gives us the two directions that we needed. We can finish this subproof and add a line. We now get Q if and only if S, and that is going to be through biconditional introduction on lines 10 to 13 for the first subproof, and lines 14 to 16 for the second subproof. Okay, so we got our not P, we got our Q if and only if S. We could AND that together now. So not P and Q if and only if S. Let's AND introduction on lines 9 and 17. Whew, we're just cruising through this. Okay, so next up is we need this whole part too. So it was overall an and so we're trying to prove the first part and then the second part, and then we're good. So we gotta get this first part. So the next goal that we have is R or P. Why should R or P be correct? Well, we might start to look at like R or S, and if we have S, then we would have P. So that's kind of an intuitive argument. Maybe we'll do some disjunction elimination on this R or S. So let's start a new subproof. We have R. We might have R. If we have R, we want to show R or P, so we could just do R or P. And so this lowercase v is how you represent disjunction. This is disjunction introduction on line 19. We need another subproof for the other case. Oh, we don't want to add, we want to start another subproof right away. We have the other case is S. So if S is the case, then we have P, and that follows from P if and only if S. So that is biconditional elimination on line 4 and 21. Okay, once we have P, we can get R or P again. R or P. And that is going to be disjunction introduction on line 22. And that finishes our proof by cases. We now have R or P, and that is disjunction elimination on this condition 2. We have either R or S, and if it's R, we get R or P, and if it's S, we get R or P. So we have 19 to 20, and we have 21 to 23. So we can check that proof, it's still good. So that gives us the R or P, and then lastly we have T implies R. So the way that you show that is generally you assume one thing and you try to derive the other. So let's assume T, and then we want to derive R. How could we find R? Well, we only really see R here, R or S, and so presumably there's some reason why the S case can't happen. And S is equivalent to P, and we have not Q. So if we have not Q, then by the contrapositive here we might think that we should get not P. If we have not P, we should think that we should have not S by this biconditional, and if not S, then R has to be what makes this true. So that's a lot of reasoning. We're going to have a proof to do here. If you have a complex proof like this that is not clear how you should go about it, you might want to just do a proof by contradiction, so that's what I'm going to go for. We're going to assume not S. Once we assume not S, we're trying to prove S. Or sorry, we're trying to prove R. So we should assume not R. Now that we've assumed not R, we have R or S, so let's do that proof by cases. So if we have R, then we have a contradiction, and that's negation elimination on 26 and 27. Then you would have S by X on 28. In the other case, we would have S, and then we could just reiterate line 30 to get S again. And thus, in either case, we have either R or S. In either R or S, line 2, we have line 27 in the case of R to 29, and we have line 30 to 31 in the case of S. Either way, we're going to have S being true. That's a lot that we've done though, so let's check that. No errors. Okay, so we have, once we have not R, we have S now. We're looking for a contradiction. We know that S is true if and only if P is true. So let's derive P, and that's by conditional elimination on lines 4. That's our P if and only if S, and line 32. And once we have P is true, we also have P implies Q. That's line number 1. So we get Q, and that's arrow elimination on line 1 and 33. So we can keep checking this, no errors. Okay, so we have Q. We also know not Q from line 3. Not Q, and that's and elimination on line 3. That's a contradiction. We have Q and not Q, can't have both. So we have lines 34 and 35 are contradictory. And now we have a very long subproof that started at not R and arrived at a contradiction. So we can finish that subproof and add a line, and we can conclude R. And that follows from indirect proof. We assumed the negation of something, derived a contradiction, and concluded the original thing. And that's on the whole subproof from lines 26 to 36. And finally now, we can finish that subproof and end that line. We have T implies R. That's just arrow introduction from lines 25 to 37. Okay, now we're finally on cleanup. R or P, T implies R. R or P, and T implies R. This is and introduction on lines 24 and 38. And finally, we had this subresult. So we want not P and Q if and only if S, all of that, and R or P. Let's write this so I can actually see it. And T implies R. Let's put this in brackets so it's clear what's happening where. And that is and introduction on lines 18 and 39. And we can check that proof. And now it says, congratulations, the proof is correct. We got what we wanted. That was a very long proof. I think I showcased almost every rule, if not every rule. And so that is going to be my demo of the OpenLogic project. Thank you for watching. I'm sorry this proof was so long. Feel free to try and craft your own examples that are simpler, or find a faster way to do this one, because I would be shocked if there is not a faster way to do this than 40 lines. I just kind of started. If you're looking for some more exercises that are a little bit more natural to do, you can click on this link here for the truth functional ones. For first order logic, when we get to that unit, you can do the exercises here. And that, I think, is everything that I have to say about the OpenLogic project.